So in this talk I'm going to discuss the addition of the regular expression operators to OCL string type and other possible string operators that could be added. Now the use of regular expressions is quite widespread in modern programming languages, and it's an important facility to validate data, to filter and transform data. And most of the languages like Java and Swift and so on provide regular expression facilities, but they differ in the terminology and semantics. And also OCL variants such as the epsilon EIL and other OCL dialects provide some partial regex support, but again they don't use a consistent terminology. Usually the most significant regular expression operator is to check whether a given string is a complete match for a pattern. For example, to validate an email, we want to check that the email matches against a pattern whereby the first part of the string is composed of alphabetic characters, maybe numeric characters as well, but alphabetic characters, at least one, followed by the @ sign, and again a block of alphabetic characters, at least one, followed by a literal dot, and then again a block of alphabetic characters, at least one. So a very simple format for an email would be like this, and we expect a valid email to completely match that pattern with no extraneous characters at the beginning or end. So what we propose is a set of regular expression operators which allow to check that a string matches against a pattern, either completely or that there is some match within the string. So there's some match for the first argument of the pattern pat, some non-empty substring of the string satisfies that pattern. And an all matches operator which gives all of the matches for a given pattern within a given string in order. Replacing matches is another very useful operation where we transform a given input string itself so that all matches of pattern are replaced by a given replacement string. And also closely related to this is we want to split a string based on occurrences of a pattern where we split on the pattern matches. Looking just at the first match could also be useful for the first match, finding the first match, and also replacing just the first match. Now, a regular expression is a very well-known concept. It goes back to almost the beginnings of computing, and typically a regular expression consists of meta characters like dot, meaning any character, star meaning 0 or more repetitions of a character or collection of characters, and so on. And we can have character ranges as demonstrated in that example, capital letters, lower letters. And the semantics of a regular expression is the set of sequences of characters which conform to that regular expression, which match that regular expression completely. And we can denote that by saying the string satisfies the regular expression S, meaning that its character sequence is in that semantic set of the pattern. So a valid email according to that pattern would be, for example, adam@eden.com. It validates each of these parts. But on the other hand, C++ doesn't validate this pattern because the pluses actually don't meet any of these characteristics. Now, given that basic semantics, we can then define our regular expression operators. IsMatch simply uses the models relation and returns true if that's satisfied. HasMatch can then be defined from isMatch by asking if there's a non-empty substring, which is a match. In fact, these two things are interdefinable. We could start with HasMatch. And likewise, all matches can be recursively defined from HasMatch. So if there isn't a match, we return the empty sequence. Otherwise, we get the first match and add that to the sequence at the beginning, and then recursively get the all matches for the remainder of the string. So for example, in this string we've got 2 matches for this literal pattern. All of the other string operators can also be defined, all of the other regular expression operators can also be defined in the same kind of recursion, and I think all matches could also be used as our basic operator, and we could define a has match and is match based on all matches indeed. So these 3 things are interdefinable. We could start with whatever's most convenient, but it seems the most natural thing to start from is match. Now, strings, of course, are very closely related to sequences. Strings are sequences of characters, so it makes sense to use some sequence operators for strings. Already in OCL we have size, at and index of. Could also use first, last, front, tail, reverse and insert at. Would be very natural things to use. And other operators like trimming and last index, prefixing, suffixing and so on could also be very relevant to include directly in the OCL library rather than in some additional external package. Now the implementations of these operators is quite straightforward, but they depend on the particular programming language, and in each language we need to define language-specific implementations. For example, in Swift we need to refer back to Objective-C facilities to do that. Now, comparison with other OCL versions. In OCL version 2.4 there isn't any regular expression support, but in other versions of OCL there have been proposals. So in EOL we have a has match, which is perhaps confusingly called matches. We have split, and we have replaces, replacing literal expressions, not patterns. In ATL OCL we don't have any checks for matches, but we have replacing operators and splitting, and replace all, but only for size 1, C and R, not for longer strings. In Eclipse OCL has got the best support. It's got is match, or perhaps it has match. It's rather unclear in the documentation, but it's one of those 2 things. And then replace first and replace all for replace first match, replace all matches, and substitute for the literal replacement. So, well, our view is that this collection of operators is both clear and comprehensive, so it's very clear what the meaning of these operators is what they actually do by their names. The names are rather long, but it's clear what they do. We could call split on matches, perhaps, would make it even more clear, but the term split is obviously very widely used and understood. Now we checked the performance of these operators, looking at some strings and various matches, checked all matches and replace all matches for a rather complicated pattern in the case of replace all matches, looking for parentheses without parentheses inside them. These end up being quite efficient, and we can see that for the largest cases the timing takes a matter of seconds for doing 1 million, even I think 10 million different matches. So in summary, we provided rationale for adding regex facilities to OCL. We defined regex operator semantics and implementations in different languages. You can have a look at an example here. Here's an example of these test cases that we did. Here's the test for all matches, some Shakespeare quotes, and the test for replacing matches, so with some brackets, and checking that we have brackets and without brackets inside them. The generated Swift code for that looks like this. It relies on the library operators like all matches and replace all matches.